Hello? Okay. Hello, can you hear me? Okay. So good evening, everyone. So unfortunately for us all, my network is a little bit unstable. So if at any point if I get out of the call, kindly send a message on the public chat. But thank you everyone for joining. So Sami Rama, and then I'll be taking the first part of our session today. Okay. So I'll be sharing my screen with our lab as well. Um, how do I do that? Hmm, okay. Give me a few seconds to share. Okay, can you see my screen? Hello, can you see my screen now? Okay, so welcome everyone. So welcome Bismarck. Welcome. Pardon me if I'm not mentioning it right. And well, as someone mentioned, will be this the second lab where we'll be looking at I'll be taking us through the norms and distance as well as the inner products part. Right. So welcome everybody once again. I think we are missing some members. So first of all, me what they learned from the class on Sunday about what a norm is. Who can tell me? Richard, are you here?
Yes, please.
Okay. So Richard, what's a norm? Or what did we learn norms, sir?
Okay, so I learned about the two types of norm. That was the L1 norm.
Mm-hmm.
That's what we call the Euclidean norm, which was
Okay.
finding the square of the vectors. Then we have the second, which is the L1 norm, which is the Manhattan norm, which was finding the adding the absolute values of the vectors.
Okay. Thank you very much. So the first thing to even ask is why are we calling them L1, L2? What does the L mean? So there's something I don't know how important it is, but then the L eventually means, let me post it here so I don't have to. It's called Levis GUI. Like, let me post it if you can see it in the public chat. I should zoom in a bit. Okay. Samuel, give me a second. Um, so this is the meaning of the L1 is called the L2 is because of the square or sorry, like the exponent that is used for it, right? So I'll be taking us through the lab session quickly. So basically, when we talk about the norm of a vector, is it better? Samuel, if you can notify me whether it's better or still okay, it's better. Okay, so basically, when we talk about the norm of a vector, right, it's literally or it's basically looking at how long, right, or the distance that the vector is from the origin, which is typically represented as the 0, 0 if we're in a two-dimensional vector space, or 0, if you're in a three-dimensional vector space, right? So as we learned in the class, we have the two types. So we learned two types of norms, which is the Euclidean ones with the L2 and the L11. So today it's how we can naturally visualize as well as compute using Python code. So let me just take us through how we actually use norms in machine learning. Right. So as I mentioned, first of all, it's using measuring distance between different data points, where as we saw during our first class, we can represent data points as vectors. Right. So it has application in if anybody has heard about KNN or clustering methods, and also how if anybody has also heard about normalization, right, where we normalize features so that one feature does not dominate. But I think in subsequent classes, we're looking at more details concerning these ones. So just for reading sake or just for information sake, right, that's why I'm giving us some of these applications or why we are even learning this in the first place. So the first is the Euclidean norm, right, where we say that the computation is where we have, let's say, of okay, so I think this formula is very familiar to us where we learned that in geometry, right? In finding the distance of a given point, we just compute the square, like the summation of the square of each of I'm coming to see like the square of each of the point that we have within the vector. So there's actually, should I say, a more mathematical expression of representing this, where we used it was landscape. Okay, now it's portrait. I don't know why. Okay, so it's not clear. Oh, okay. Let me see. I think because I'm zooming in, it's clear though. Okay, okay then. Okay, sure. So can I proceed? I think I'll have to get a picture of that. So let me just share a picture of that quickly for us. But we know the Greek alphabet sigma, right? So instead of representing it with the long or the breakdown of everything we have, there's a more mathematical way of representing it. Let me quickly share that as well in the chats. Where am I not? How to find this? 2 seconds. Nope. Okay, this is. Is it possible to paste pictures? I think so. It's possible. Oh, okay. So this is representing it like with sigma, and then I know I hope with this notation. Is anybody familiar with it? So it's basically this formula that has been brought this way or put in this form, but then here's n here, and then no, n here is the same as the n here, and then sigma is basically the summation of like each, like the square of each of the points. Any a simplified form of the standard form. Is that clear? Is it clear, everyone? Anabi, Bismarck, Chukuneta, Richard. Okay, if it's clear, then let's see. Okay, so this is a simple function that was used to use in order to compute, right? So then after a function f L2 norm, Let's me try some examples quickly. Oh, and your representative vector back. And how this should be with
Oh,
so how you find a hello. And I mean, please mute your mic. Okay, thank you. Oh, screen sharing has ended. Okay, share. Okay, well, this one went out. Sorry, I've been notified about something. Yes, please. My boss has notified me. No problem. So, anyways, the first part is we define, and then you've assigned a variable with an amount of 0, right? So this variable will tell the distance we calculate, right? So since you are familiar with for loops, I assume you're familiar with for loops. But if you are not, just let me know so we can quickly walk through it. Are we all for loops? Are we all familiar with for loops? So we move quickly. Anabi, Bismarck, Emmanuel.
Yeah, I'm familiar with follows.
Pardon me, I missed you. Whoever spoke. Awkward silence. Too awkward. Okay, let me just assume that everybody follows. Okay, so let's proceed. Right. So within this for loop that we created, for me, so this is the case we have now. All right. So for every for loop that we have, where we see the total being stored with x exponent 2, which is basically x squared of every value within our vector v, right? So after this is computed and then stored within the variable called total, then we will now come and find the square root of the distance that we calculated, which we are storing the variable called total. Right. So in this example, we saw the 3, 4 as the variable that we have. So as the variable we have, or the vector that we have, right, where we are finding we are trying to find the L2 form.
I need your support because
Hello? Said at all that's being asked, and we can address all issues. Okay, so is it the issue is that somebody has some issues with some of the fundamentals of Python? Okay, so send all questions here. Chat, you can answer them as we move. So I think Velma had a question. So, Samuel, should I proceed or I should get a question first? Questions? Okay, sure. You can spend some time. Okay, sure, sure. Thank you. Okay, so then this was one form where we're using just plain Python to get the L2 norm, right? But with this example, we have a certain Python module called math, right? So with the math module, it's basically a module with different functions, inbuilt functions, including like square roots, etc., right? Which will prevent you from typing x star star 2 or x star star 0.5, right? So it's basically functionalities, functions that are more, shall I say, instead of typing them in plain Python, this module gives you some functions that have already been defined, right? So for example, we see this math dot square root of s. So s here is the total that we had here, right? So representing this s to be the total of the distance that we are going to calculate, or the L2 norm. So for v, which is for every data point, or for every, shall I say, for each value within a vector, right? We get, or we do the computation, which is basically the square of it, right? Where we then assign the total to s, which was, or which had the initial value of 0 here. Then now use the square root function, which is in math, right, to now compute our norm, which is basically the square root of what we calculated here to be s. Right, so we use the same example here, which for the vector 3, 4, and then we got the same answer as well, proving that indeed we can also use math dot square root x s instead of using total exponent 0.5 as well, right? And again, finally, we also have the option of using NumPy, where I'm sure we are familiar with NumPy from our previous lab, or lab 1. Right. So with NumPy, it even makes the lines of code much, much, much simpler or shorter, where we only have about 4 lines of code. So in NumPy, get the Yes, I'm in. I think I missed that. Okay, I can hear you now. But any questions? Any questions? Any questions from anyone? Any questions with what we've done so far? Any questions? Any questions? You can't explain again. Oh, I can proceed. Okay. Okay. Mhm. Bother. I'm sorry. Please, could you type for me? Can you type for me today? Never it comes and goes. Yeah, right now it's at exactly 1 bar. So okay. Oh, okay. You're not good type and listen. Sounds so Samuel, is it permitted for them to? I'm thinking they can even have access to. I can give them this mini exercise on their own and give about 3 minutes for them to like give their responses. Can I do that? I was thinking of since we have some. Okay, can I give them access to a question, like a quick quiz within the chat, and then 3 minutes to type out their code? An assignment will come. Okay, sure. You said okay. So, very small. Okay. Then okay, Mano. So questions will come. Questions or trial questions will come after this lab with like a lab note to try out. Okay, so moving on to the Manhattan Project. Anytime I hear the Manhattan name, it's more so the Manhattan Project. But don't mind me. Let me focus. So with the Manhattan norm, right? You basically down is just addition of the points within a vector. Or let me call it data points because of what you are doing. Right. So with the Manhattan norm, the logic behind it was so working this risk is just the addition of all the it's basically like the addition of all the data points within the vector, right? So you are measuring the distance by summing the absolute steps along each axis. So for each axis, right, you add or you sum the absolute steps for like along that particular axis. So let's have an example. I think my time is almost up, so I can't do much. I think an example can help us as well. So we have a simple function here, which is being used to compute the Manhattan norm, right? And the Manhattan norm, as we are doing, the focus is eventually to apply it for machine learning, right? Is that it can be used in something known as the lasso regularization. Right, let me type it here. So something known as this. I think along the way we'll learn more about it. So what it does, or the point of using this kind of regularization, right? It's to the end that it actually makes some weight exactly like zero, right? So about weight, U1, all of those ones later on. But then it has like applications in feature selection eventually, which is very important when we are doing any machine learning projects because features or how good your features are eventually affect how efficient your model is, right? So this is just something you can read along maybe later in your time, your spare time, about what this Manhattan norm is used for practically in machine learning. So as you can see here, function. So we again define a function as L1 norm. This V here is representing the vector inputs we are going to put inside the function, right? And again, it's going to be a summation. We use the variable total and we equate it to zero, right? Because eventually we'll put the summation of um, our data points within, or we'll store it within this particular variable. So again, we use a for loop so we don't have to type addition one by one, right? Where we say for each x within our vector v, right, there should be a computation, which is this absolute, or it should find the absolute value, which is the positive, let me say the positive form of every single data point or every single value within our vector, right? And it should sum each one of them and then now put it in a variable called total, right? Then afterwards, this function should return the total, which is equal to the summation of every single um, positive value of the data points of the values within our vector v, right? So that is what this function will be outputting with the total, which won't be zero, but then the every absolute value of x. So like v which had 3, negative 4, right? Let's visualize it. Get the L1 norm, that's a norm. So just a negative function called the L1 norm. So let's try and do it even manually. So we have 3, absolute value of 3 is 3, absolute value of negative 4 is what, 4. So 3 plus 4 is what, 7. So that is why we got the value of the norm to what, to be 7, right? And again, we did the another form using NumPy. So NumPy gives this function called sum, and again we see the value option here, the absolute method here also available in NumPy, right? And we use the same vector 3, negative 4, and again we have the answer 7. Exactly. Any questions from here? I think my time is running out. I have exactly 24. Oppenheimer, you're not done. Oh, okay. Which one? Uh, so I should take my time. any questions for the Manhattan project? Sorry, Manhattan, no. Any questions? Any questions before we move on? Like, any questions? Any questions? Any want to just send me a thumbs up with the reaction, like something like this, so I can know whether to move on or not. Okay, no response. I think I'm going. I'll give a thumbs up for Nabi. Miss Monkey's out. Shira, Emmanuel. I have 22 minutes. Ooh, sweet. I'll speed up. Small. Okay, I don't want to finish all for my students. Any questions? Okay. So I will assume that everybody's fine, hopefully. But if there's any questions along the way, so that I can address it even after or when we have a break for asking of questions. So quickly, this one, which is basically the distance between, which is also known as the Euclidean distance, right? So the first L to the or the norm that we computed, that was for a singular vector, right? But then we can also compute the distance between two vectors, which is also known as an Euclidean distance, right? But with that one, instead of doing the square of each point, because we have 2 points, right? We basically, let's say we are representing the vector as A and B, right? So we find the, shall I say, the difference between each point. But then first of all, they should be, or they should have the same dimension, right? Before we can do that particular computation. Right, that one is very, very, very important. We can't compute the distance between them if they don't have the same dimension, right? So assuming that the two vectors A and B have the same dimension, then this computes the Euclidean distance between them. Where again, okay, that one is not very neat, so I'll not talk about it then, right? Where we use the difference between them, then we sum up the square of the differences of each of the data points. So I think this example can give us a better understanding of how to go about the Euclidean distance for 2 points. So you have the total, it's created this function called the Euclidean distance, and then we have the two parameters, which is the two vectors you are going to use, right? And the total, again, another variable called total, which we are using as 0, which will store the Euclidean distance between the 2 points here, which is for I in range L of A. Um, do I have to really explain this? Do they have Okay. Thank you very much. Sorry about that. Okay, thank you very much. So, this again, what the Euclidean distance is, right? So this is the representation in normal Python, right? So it is for I in range len of A. So it's basically telling us about the okay. So len of A is about the length or the number of, should I say, points within the vector A, right? So if we do for I in range len of A, so we are finding the this or the number of data points within A, right? And then I is for every value, or this eventually this sequence is that for each I in where I is basically like sorry. Let me to explain it very simply, right? So imagine if maybe A has like 5 different points, right? I so ln of A is right. I will be a number within 1, 2, 4. Right. Those will be the values. So I will be a number between 1 and 4, just 1. Okay, no, that will be 0. 1, 2, 3, 4, 5, 6. It's supposed to be 0. Sorry. So I will be from 0 to 4. Right? And number between 0 to 4 is 0, 1, 2, 3, 4. So here we now put in that for each I in range len of A, right? It should, or we should find the total of A for, we know about index, and I think someone said we all have some basic knowledge in Python. So I am working with that assumption. But if you don't get anything, send me a text in a chat so I can explain and take my time. Right. So we do the index for A, we do the minus as well for vector B, and then we now count square of each one of them, and then do the summation using this function here, O2, and then it will store the summation of the difference of the square of the difference between each point within the vector within the variable called total, right? Then we now find the square root of total using, okay, I think there's a text. Zoom in your screen. Oh, sure. Sorry. Is it better now? Okay. Hopefully, I think it's better. Hopefully, it's better. So that was the computation we did here for this example, where we had 1, 2, B, 4, 6, and we found the Euclidean distance to be 5, right? After passing the vectors that we had into this function we had created. So then again, we expressed it in NumPy instead of plain Python like we did here, right? And we used remember this method. It came along when we are doing, okay, it came along when we are actually doing the L2 norm, which we did earlier, right? And again, Whew, finally, I'm back. Goodness. Fucking seriously fucking. Pattern distance. What was the last thing Samuel? This thing I got to before I zoomed out. Total. Okay. I can the graph. Wow. Really interesting. Okay. But I hope you this one. Okay. So for right, this was a simple visualization of the concept, right? Where we use matplotlib and NumPy. But I'll not go through the code. I've actually sent us a code to visualize as for if you are running along, if you are typing along with us. Right. So that was a code I sent earlier. So you can visualize how it looks like with the data points that we had, which was the A and B that we used. And again, with the Manhattan distance between 2 points, we have the same computation that we have, which again the summation of the individual points within the vectors, right? The absolute value of the difference between them. Then we compute. We had this example. I think I was 7 minutes more. So yeah. So we did our computation as well. But if there's any confusion here, let me know. Oh, so long ago. What? That was painful. Zoom in. Okay. Thank you. Too zoomed. Wow. So, so this was using NumPy for calculating the Manhattan distance as well. So again, this short or a simple visualization for the Manhattan distance. So as you can see, look at how it goes from here. I start from 1, 2, then I journey all the way to 4, 6. So like we mentioned, the Manhattan is basically walking along the streets, right? I don't think any street is this way, diagonal, right? So we walk along this line, walk along this line. Is that fine? So from 1, 2, then we go to 4, 6. So again, I'll send us code so we can visualize it. If you are okay. So of course, I mean, why not? We have this mini exercise to try just in case you miss so you can try and then send us with what we're able to later in addition to yeah, in addition to the lab session, the lab notebook that we'll be sharing with you. So yeah, again, connection. I think I've already spoken about that. Basically, turn off is okay. So hopefully you can hear me. Let's proceed. Any questions with regards to the norms for the L1 and the L2? Any questions so far? I don't think someone can help us. Any questions before we move? Mm. Someone extremely noisy from your end. Okay, thank you. Any questions before we move on to the next section? Any questions? If there are no questions, kindly give me a thumbs up. I think insurer. Any if there are no questions, give me a thumbs up so I'll know to proceed. Any questions? Any questions? Any questions? Okay, I don't think there are any questions. And it's still some awkward silence. So it definitely falls for this one. No awkward. Right? Awkward silence. Too much. Any questions? Okay. I don't have time. 1 minute. Okay. Session is the inner, right, which we learned during the class. So when we talk about the products, let me look for a very simple explanation. How do I even simply? Okay. So let me just use the explanation here without having to be too simple. Right. So how much? So it's also not a dot product. I think we did something like that by SHS. Right. Is a zoom fine? Yeah, zoomed enough. Right. So it's basically measuring how much the vectors, right? And typically it's using two vectors. So we are assuming we are using two vectors, right? So it's measuring how much those two vectors align or how similar their directions are. Let me see. Okay, no too much explanation. Okay, so how similar like their direction and how much those two vectors are within the same or not, right? So if we have a very large positive inner product, right, it means that the vectors are pointing within the same or in a similar direction, right? So remember that vectors have both magnitude and direction, which is like the typical explanation here for vectors. So you compute the int or the dot product, realize that the value is 0, right? Then it means the vectors are orthogonal or perpendicular. We'll go and data, which means that basically how the vectors are aligned is such that they are literally like this, right? And if they're negative, then it means that the two vectors are opposite direction. Because remember that we said the dot product is between how much these similarly were directed, right? And again, there's a high caution for us. Or we have the same dimension. So class about this format or way of calculating the dot product. So I'll not talk much about it. So for two-dimensional vectors, there's a computation where we have v1, v2 for one vector and then w1, w2. So Samuel, I'm wrapping up very soon. So we do the computation so that we multiply the two, so the first two, and then we add the product of the next data point. And we do the same thing for like 3D vectors. That's why we have this general notation, sigma, and then the product of the two. So that's how we represent it in Python, right? This is how we represent it in Python. So we have created a function with the dot products, and we have v1, v2 representing the two vectors. Again, we have total equal to 0, each x and y, which is in zip of like v1, v2, which is just multiply like for this zip will literally should I say it help it to match each data point within the same line, right? So that there will not be that x and y will be like different data points in different points or different eventually multiply. It told me this multiply by this, summed with this, multiply with this, right? That is why we have this part within our code. Right, so for each x and y in zip v1, v2, we find the total of each of them, right? The total of the product of the two of the values. Then we return the total. So for this one, we use a three-dimensional vector for v1, v2, since they have the same dimension. Then, yes. So we did it manually aside within our code, and we had 32. And after doing the computation too, we actually had 32, meaning that our function is indeed accurate, right? And then again, we used the NumPy format, which is here. So NumPy has a method called dots, actually does the dot product for us without having to manually type all this, right? So it does that manually, whether it is three-dimensional, two-dimensional, four-dimensional. The dot method will compute the dot product for us. So again, we had 32, meaning that this is functioning properly. So we did some more examples. Yep. So we added this condition. I hope you know about if functions, right? We added this condition to ensure that the condition we have, which is that all vectors must have the same dimension, is checked before it even goes ahead to execute the function result. Right. So we did that again with another example, which two-dimensional vectors v and w, and we had 11. Right. So we did the same thing again using the NumPy method. So, uh, okay. So this is a fun fact to know, right? That let's say we have a vector v1, v2. They come three-dimensional, four-dimensional, right? If we find the dot product of that vector itself, right, eventually going to be v1, v1 going this way. So let's say, for example, I have a vector v, which is 3, 4, right? If the v again, aligning it to be v again will be 4. So eventually v1 is 3, v2 is also 3, right? So you find the square of each of the numbers, you find this. And then you remember that the Euclidean norm or the length, which is L2 of the vector, is also the square of the v1, v2. So eventually, right, we find out that the dot product of a vector with, right, is this the square of the Euclidean norm or length of the vector. That is something to know. To have some both. So questions, axioms. Um, confirm something. Any questions? If I'm speeding up, to let me know. I'm actually assuming a lot of, so if I'm speeding much, I think time is up. Someone or stick. Okay, discipline. So I'll have to get another go through the inner programs in 1 hour. Concept. These are all the things I'm supposed to go through before. I will spend time later where we can go through inner products, axioms as well. So Samuel, you can take over your section part. So thank you, people. Do you have any questions before I hand over to Samuel? That's not satisfying. Any questions before I move on? Samuel, that's Yeah, if I hand over any questions for me. Thelma, I don't know if you're speaking, but I can't hear you. Hopefully you can hear me. So if for me, if you could send a message that means I want to ensure we are not missing any questions from anyone. So questions to then kindly give me a thumbs up so I can hand over to someone. Okay. So I ended before the axioms. Yes, hello. Hello. I ended before. Yes, hello. Can you hear me?
Lenka, Lenka no